Welcome, ladies and gents, to our problem-solving video on the conservation of momentum. Now, first off, just taking a look here at some refreshers, we should remember from our previous videos that an elastic collision is a collision in which we start separate and end together. That means the equation is going to have four different velocities, meaning the velocity of each object before they collide and the velocity of each object after they collide. Realize that at all points these objects are separate from one another, meaning that they have their own velocity. The next type that we have is a perfectly inelastic collision, and in this collision we start separate but end together. So in the beginning of the problem, initially, each mass has its own velocity, but at the end of the problem they become entangled or stuck, and they share some final velocity. Last but not least, here we have recoil, which is where they start together and then end separate. So they share some initial velocity, but at the end of this type of collision, which is often an explosion or a firing of a weapon, they have their own final velocities. So we have m1v1 plus m2v2. All right, so let's get right into it. The first problem that we have here goes as follows. It says a 0.2 kilogram cue ball traveling to the right at 3 meters per second collides head-on with a 0.2 kilogram 8 ball. So right here, since they're colliding towards one another, we know that they're starting separate. So I want to kind of make note of that. So they start separate. Then, if I keep reading, the 8 ball was initially at rest. After they collide, the cue ball moves to the left at 1 meters per second. How fast and in what direction will the 8 ball be moving after the collision? So that means that they also end separate. So in this type of collision, if they start separate and end separate, we know that it is elastic. So now we can begin writing out our equation and solving. So I like to always separate my initials and my finals. And basically what I do is I write my elastic collision. Initially speaking, we have m1 v1 plus m2 v2. And then after, finally speaking, we have m1 v1, meaning mass 1's final velocity, plus mass 2 times its own final velocity. Now we want to go through and decode the problem and plug in correctly. So taking a look, we know that mass 1 can be considered our cue ball, 0.2 kilograms, but mass 2 actually is the same value. It's also 0.2 kilograms for our 8 ball. Continuing to read through, the cue ball starts at 3 meters per second, so let's go ahead and start to fill this in. Our mass 1, which is 0.2 kilogram cue ball, starts at a speed of 3 meters per second. Now I want to add to this the momentum of the 8 ball initially, which is our 0.2 kilogram 8 ball, but it's initially at rest. So that means this whole term is actually going to cancel. It's going to become 0, because v2 in this instance is 0. Now on the other side of the equation, after they collide, it tells us that the cue ball moves to the left at 1 meter per second. So careful, it's still our mass 1, so this is 0.2 kilograms. Now its new velocity is 1 meter per second to the left. But just noting, initially we were traveling to the right, I have to denote this in some way, and I'm going to say that our final velocity here for the cue ball is negative. Now just finishing this off, we can plug in our 0.2 kilogram mass for our 8 ball times its v2, or its final speed that we do not know. So now solving, you can simplify everything here. This becomes 0.6 kilograms times meters per second is equal to negative 0.2 kilograms times meters per second plus 0.2 kilograms times our v2, which we're looking to find. If I add over this 0.2 kilograms times meters per second, I get 0.8 kilograms times meters per second is equal to 0.2 kilograms times v2. Last but not least, you can divide these values, and what you end up with is that v2 is equal to 4 meters per second. Notice it's positive, meaning it's going to travel towards the right. Okay. Number 2. A 1,500 kilogram car traveling east at 20 meters per second collides with a moving truck of a moving 2,500 kilogram truck. So this vehicle is moving. After they collide, the two interlock. Okay, this should be a hint right there. And it says they move together with a velocity of 30 meters per second to the west. So, taking a look at this, if they move together in the end, that means they started separate and end together. This tells us that this is a perfectly inelastic collision, or to abbreviate, PIC. As a result, I can look back at my equation, and that tells me that they start separate, so it's m1v1 plus m2v2, each of their initial momenta, is equal to m1 plus m2 times their shared final speed, vf. So going ahead and substituting in my values, I get a 1,500 kilogram car traveling east at 20 meters per second, meaning moving to the right. So let's use a positive 20 meters per second. Collides into a truck that's moving, but we don't know its speed. So we have 2,500 kilograms times v2. And this is still on the initial side. Sorry that this kind of got dragged over. Now, after the collision, we know they share a speed of 30 meters per second to the west. So if I add together their masses, I'll get 4,000 kilograms times their shared speed of now negative, because it's westward, 30 meters per second. So, solving here, 1,500 times 20 meters per second gives you 30,000 kilograms times meters per second of momentum, plus 2,500 kilograms times our unknown speed, v2, is equal to negative 120,000 kilograms times meters per second. So now solving this, we need to go ahead and subtract over the 30,000 and then divide by 2,500. Essentially what you're going to get is 2,500 kilograms times V2 is equal to negative 150,000 kilograms times meters per second. Then dividing by the 2,500, we'll get a V2 is equal to negative 60 meters per second, meaning the truck was initially traveling westward at 60 meters per second. Okay. Number 3. Two sumo wrestlers run towards each other. The first has a mass of 150 kilograms and is running at 14 meters per second. The second has a mass of 200 kilograms and is running at a speed of 18 meters per second. If the first wrestler bounces backwards, find the final velocity of the second wrestler. Now, if you carefully read through, what you'll notice is they were each moving in the beginning separately at their own speeds. And then the second wrestler, or rather the first wrestler, bounces backward at its own speed after the collision. Therefore, at all points, our objects are separate. So they start separate and end separate. This is important because this tells us that this collision is elastic. So what I can do is I can set up that initially I have m1v1 plus m2v2 is equal to, finally, m1v1 plus m2v2. So now substituting in, they're running head-on at one another. So if you notice, if they're running towards one another, that tells us that their velocities are actually opposite. So I'm going to say that the first wrestler is moving in the positive direction. So I'm going to write in for this first wrestler that this one is 150 kilograms times a positive 14 meters per second. Now for the second wrestler, I have 200 kilograms times 18 meters per second. So just underlining those values. Realize that our second wrestler of 200 kilograms is traveling in the opposite direction, so negative 18 meters per second. The first wrestler bounces backwards, meaning he changes his direction. So if his initial velocity is positive, his final velocity needs to be negative. So I have 150 kilograms now after the collision, traveling at negative 6 meters per second, which will help me to find the final velocity of the second wrestler, v2. Okay, now plugging in and solving. If you notice here, first we have to multiply everything together, so you end up getting 2,100 kilograms times meters per second for the initial momentum of the first wrestler. And then since this actually has a negative, this is going to become a subtraction. It's going to be minus 3,600 kilograms times meters per second for the second wrestler. And then on the other side of my equation, I'm going to have negative 900 kilograms times meters per second plus 200 kilograms times v2. So now I want to move everything over to the left side because my variable here is on the right. So if I just simplify these, this is going to become negative 1,500. And then if I add 900 over to it, I'm actually going to get a negative 600 kilograms times meters per second is equal to 200 kilograms times v2. Notice I skipped a few steps there. I kind of combined these together. Last but not least, though, if we divide by 200, our v2, or our final velocity of the second wrestler, is going to be negative 3 meters per second. Now be careful, since we weren't actually given any directions in this equation, this just means my negative represented that the second wrestler is traveling in the same direction as they were initially, if you compare it to the negative 18. However, they lost 15 meters per second worth of their speed. Right now they're only traveling at 3 meters per second. Okay. Last but not least, number 4. Number 4 says a 4 kilogram gun shoots a 0.1 kilogram bullet at 400 meters per second. Find the recoil speed of the gun. This one couldn't have even more blatantly stated. What type of problem is this? Well, it's recoil. Now, your first hint was that it was a gun firing a bullet. Now, even more so, it comes out and asks for a recoil speed or a recoil velocity. So how do we figure this out? Well, if you notice, there's really not that much information given in this problem. We have m1 and m2, and we have a speed. Let's write out the recoil problem and then think this through. So it's m1 plus m2 times their shared initial speed, vi, is equal to m1 v1 plus m2 v2. And you might be thinking, wait a second, it never gives their initial speed. Now, for any recoil problem involving a gun, their initial speed is typically at rest, meaning you can think of the gun and the bullet as being stationary before the trigger is fired or pulled. So as a result, that makes this whole left side of the equation 0, because the bullet is just stationary with respect to the gun. So we get 0 is equal to, now let's piece this together. Our 0.1 kilogram bullet leaves, or on the final side of our equation, leaves with a speed of 400 meters per second. I'm just going to call that the positive direction. We'll call the recoil direction as negative. And let's add to this now the mass of the gun, 4 kilograms, times its final speed, v2. So essentially, if you notice, since this whole left side canceled out, we're actually going to have to move over the momentum of the bullet to then solve for the speed of the gun. So just solving this out, you get 0 is equal to 40 kilograms times meters per second plus 4 kilograms times v2. Now, for those of you that are good with mental math, you might already realize what v2 is, but subtracting over, you get negative 40 kilograms times meters per second is equal to 4 kilograms times v2, meaning v2, or our recoil velocity, is negative 10 meters per second. This is the speed that the gun experiences, or this is the kickback, as we sometimes call it. All right, ladies and gents, that concludes our problem-solving video on conservation of momentum.